Writing in Python or C feels like giving a computer a list of steps to follow. You start at the top, and the processor works its way down, one instruction after another. But a silicon chip contains millions of individual pathways, and every single one of them is active at the same time. There is no single line of focus. When a signal enters a chip, it doesn't wait for a previous operation to finish. It triggers every gate in its path simultaneously. This creates a unique design challenge. The text on your screen is sequential, but the physics of a microchip are parallel. Engineers need a way to describe that three-dimensional web of concurrent electrical signals using standard lines of code. Verilog was built to solve this. It serves as a functional blueprint for chip architecture, providing a text-based syntax that maps directly to the physical layout and timing of electrical signals. Because hardware either lets electricity flow freely through logic gates or traps it inside memory cells, Verilog splits itself into two distinct worlds. Each physical state is controlled by its own specific set of rules. The very first world is combinational logic. This describes a physical system where the output is determined exclusively by whatever is happening at the inputs at this exact millisecond. To model this instant, continuous reaction, Verilog uses a dedicated tool called continuous assignment, driven by the assign keyword. Take a basic operation like an adder. You use the assign keyword to link inputs directly to an output, like assign sum equals A exclusive or B. The simulator treats assign statements like physical copper wires. Always active, an input change instantly updates the output. However, continuous assignments have a limitation. They cannot hold a state. If the signals feeding into those inputs stop, the output vanishes immediately. This makes a system without memory unable to perform complex, multi-step tasks. Without a way to retain data over time, hardware can only react to the present moment. To remember the past, the system needs a heartbeat. That is the role of the computer's internal clock, synchronizing the chip to a repeating rhythm. This is sequential logic. To build hardware memory, Verilog groups instructions inside an always block, which is programmed to trigger only on the edge of that clock pulse. Inside this block, we use the non-blocking procedural assignment, represented by a less than sign and equal sign. This operator evaluates all incoming signals on the right simultaneously. It holds data in a temporary state, pushing updates to the left only when the time step ends. This delay prevents race conditions. If millions of memory cells updated at slightly different times, a signal could accidentally overwrite another before the clock pulse was finished. By forcing a synchronized update at the end of the step, the non-blocking operator allows the simulator to perfectly mimic how hardware registers snap and hold data. These two paradigms define the architecture. Assign handles the instantaneous flow of signals, while the non-blocking operator manages synchronized memory. This RTL schematic shows those words turning into silicon. Continuous assignments become combinational logic, like the OR and NOT gates on the right, reacting instantly to voltage. The non-blocking assignments manifest as sequential state registers, like the yellow block, locking voltage securely in place. This mapping makes Verilog a direct translation of electrical physics. A designer describes the behavior of a gate, or the timing of a clock, and the language provides the exact syntax needed to represent that physical reality. Distinguishing between continuous flow and procedural memory is the foundation of chip design. These two rules keep our digital world synchronized and moving.